Good afternoon, everyone. My name is Jung Lee from UNIT in South Korea. I will present about safe trajectory planning with Bernstein polynomials under control function constraints. Here is what I'll cover today. I'll begin with motivations and contributions and go over the background and methodology and present about simulation results. Autonomous robots are operating alongside humans in restaurants, hospitals, and urban environments. This requires robots to simultaneously ensure obstacle avoidance and goal reaching. However, existing control function-based model predictive control often suffer from high computational cost, limiting real-world deployment. Our framework addresses both safety and computational efficiency in a unified way. Instead of enforcing safety at every prediction horizon, we parameterize trajectories using Bernstein polynomials and constrain only a few Bernstein control points inside a safe corridor. This leads to two concrete contributions. First, we reduce safety constraints. The complexity no longer scales with the prediction horizons. And second, this enables real-time performance up to 10 times faster than existing baselines while maintaining comparable success rates. First, let's define what safety means for a robot. We define the safe set as S, where H measures the safety. If H is positive, the robot is safe at the state X. If H is 0, it is on the boundary. And if H is negative, it becomes unsafe at state X. Our goal is to keep the robot inside the safe set all times. Based on Nagumo's theorem, the idea is simple. At the safety boundary, the system should not move outward from the safe set. A function h satisfying these conditions is called a barrier function. Now, let me introduce control barrier functions. To generalize Nagumo's theorem to the entire state, we require these conditions where alpha is strictly increasing class kappa function satisfying alpha of 0 equals 0. Intuitively, near the boundary, the robot must move carefully. Inside the safe set, it can move more freely. For discrete systems, the safety margin can decrease, but not too fast. Now, to implement the control barrier function condition, we need a trajectory representation that is smooth, analytically tractable, and computationally efficient. Bernstein polynomials satisfy all of these requirements. A Bernstein polynomial is defined by control points, basis functions, and polynomial degree. Basis functions determine how much each control point contributes to the trajectory. And for defining the d-degree Bernstein polynomial, we need d plus 1 control point. That is, the Bernstein polynomial is formed by weighted combinations of d plus 1 control points. So the entire Bernstein polynomial remains inside the convex hull of control points. Here is the overall pipeline of our framework from observation to control. Today we will focus on the safety guaranteed trajectory planning module, which is built upon control barrier functions and Bernstein parameterizations. For building on the control barrier function condition, we construct a safe region called the safe corridor polytope. The process has 3 steps. First, the robot detects nearby obstacles. Second, for each obstacle, we separate a half space that keeps the robot on the safe side. Finally, we intersect all half spaces to obtain the safe set. Each half space is defined as a control barrier function, and each intersection forms the safe set. And our key question is, how do we ensure the trajectory stays within this safe corridor at all times? If all Bernstein counterpoints satisfy the safety constraint, then by the convex Hurd property of Bernstein polynomials, the entire reference trajectory is guaranteed to remain within the safe corridor. From the contour-barrier function condition for discrete time systems, the nonlinear model predictive contour with contour-barrier functions infers safety at every prediction step k. This induces n-safe constraints for a single obstacle. So the total number of constraints becomes OMN. It scales poorly with prediction horizon length. This is where our method comes in. Instead of enforcing the contour-barrier function conditions at every prediction step, we enforce the contour-barrier function conditions only on the d plus 1 Bernstein counterpoint. Since the polynomial degree d is much smaller than the prediction horizon n, we use far fewer constraints, leading to significantly faster computation. So far, we have ensured that the reference trajectory is safe, but here is an important question. Even if the reference trajectory is safe, can the actual robot perfectly follow it? In practice, tracking error is unavoidable. We assume it is bounded. To account for this, we tighten the safe set by eroding it with a ball of radius epsilon. By planning the reference trajectory inside the tight set, we guarantee that the actual trajectory remains within the original safe set S. However, this approach comes with limitations. It requires an accurate estimate of epsilon, which is difficult to obtain in practice. It reduces feasibility, as the tightened set may become too small, and it leads to conservative behavior when epsilon is so large, keeping the robot unnecessarily far from obstacles. The four videos are our simulation results. The left two videos show static obstacle environments, and the right two show the dynamic environments with moving obstacles. For handling moving obstacles, long prediction horizons are needed, and safety has to be checked quickly to react in real time. There is a fundamental trade-off in choosing the prediction horizon. A longer horizon improves foresight but increases computational time. A shorter horizon is computationally efficient but can lead to short-sighted behavior. Balancing this trade-off is a key challenge in real-time nonlinear model predictive control. These two graphs summarize our simulation results, the left for static scenarios and the right for dynamic scenarios. The line represents success rate and the bars represent solve time. We compare against two baselines, IUMPC and nonlinear MPC with discrete CBF. As you can see, our method achieves the lowest computational time across all prediction horizons without sacrificing success rate. More importantly, as the prediction horizon increases, our solve time remains relative constant where the baseline scales significantly. This figure provides a broader comparison across all methods. Our method consistently appears in the top right region, achieving both high computational efficiency and stronger safety simultaneously. Looking at the baselines, nonlinear MPC with discrete time CBF-based methods are computationally efficient but lose safety at short horizons. On the other hand, IMPC-based methods maintain relative higher safety, but it have a significant computational overhead. It is a summary of our work. First of all, our framework is safe, By using the convex hull property of Bernstein polynomials, we guarantee for the invariance for the safe set. Second, it is fast. The computational time becomes independent of the prediction horizon. In short, our framework is safety guaranteed, computationally efficient, and ready for the real world. Thank you for your attention. I am happy to take any questions.